So let's look at ionic compounds. Metals bonding with nonmetals, electrons are transferred from the metal to the nonmetal. We get a cation and an anion, and the attraction between them results in a compound. And so in Lewis theory, what we do is we represent this process by moving the electron dots from the metal to the nonmetal. So let's try that. Write Lewis structures for potassium and chlorine and show how the electron transfer, that happens when they bond. So potassium is K, and how many valence electrons does potassium have? It has 1, because it's in group 1. And chlorine is Cl, and how many valence electrons does chlorine have? 7. 1, 2, 3, 4, 5, 6, 7. So I look at these and I see that neither of these atoms has an octet. That's what they're trying to get. So chlorine just needs 1 more electron. I tend to personify atoms because it makes it just, I don't know, more interesting. And it seems easier for me to remember than trying to think about the hard science behind it. But I look at chlorine and I think about chlorine saying, man, if I could just get 1 more electron, I'd look like argon, and maybe I could get invited to the party because that's where all the cool kids are going. I just need 1 more electron. And potassium's sitting over here thinking, man, I've got this extra electron that's preventing me from looking like argon. Because let's look real quick at the electron configuration for potassium. So it's 1s2, 2s2, 2p6. We've gone through the second row. We need to go into the third row. 3s2, 3p6, 4s1, right? So this right here is potassium's 1 valence electron. If we get rid of that, what are the valence electrons? Now the third level is the highest one, and there's 8. So if I peel off this 1 electron, underneath, I've also said it's a little bit like an onion, we've peeled off this little bit of layer, and underneath is a nice unbroken layer of onion skin. So the metals are doing that. They're peeling off this incomplete layer. They've got like 2 or 3 electrons there, and it's easier to take those off than try to fill it in. So potassium's saying, man, if I could just get rid of this electron. Well, you know, right next to him is chlorine, and she's trying to get an electron, and so a transfer occurs. Potassium's trying to get rid of the electron, chlorine's trying to get the electron. So we just move it over. Now chlorine has 8, and it looks like potassium has none, but that's because we just peeled off the outer layer. When you do that, underneath is a full layer. So we peeled this guy off, and now there are 8 valence electrons. Are we going to draw dots in there? No, we're not. That will get very confusing. When we draw Lewis structures, we move dots around, but we don't bring out any of the other electrons. The number of dots you start with is the number of dots you end up with. Now this has caused there to be a charge on this atom. Right? By losing an electron, the potassium becomes positively charged and the chlorine becomes negatively charged. Now all of a sudden these guys are looking pretty attractive to each other. Positive and negative, opposites attract. When we draw this symbol with a negative sign, you can probably imagine how that negative sign could get lost in the dots. And so what we usually do is we put brackets around the part with the dots, and we put the charge on the outside so that it doesn't get lost. You don't need to do that for a positive ion because it's lost all of its dots, and so there's nothing to be confusing about. Any questions? Yeah.
So would there be any situation where this wouldn't work as far as like pairing to the atoms?
Would there be a situation where this wouldn't work? It doesn't work between two nonmetals because they're both trying to get electrons. And so one isn't willing to give an electron, transfer an electron to the other. It won't work with two metals because they're both trying to give up electrons. But we'll find that with the nonmetals, there's another way. Between metals and nonmetals, it's not always as simple as this has one to give up and this needs one, and so it just takes one atom of each. Sometimes it's more complicated. One has two to give up, another needs three, and so it takes a group of them to get together. Does that answer your question?
Like a group of, like let's say for example, in this case, it would be like 2K needed.
Right, if you're doing like sulfur that had a 2- charge, you'd need two potassiums to fix things up. And we'll do an example like that. So in that situation, the chloride ion has an octet. The potassium ion lost its only valence electron. It's left with an octet in the shell underneath, which has now become the valence shell. We write the Lewis structure of an anion within brackets and the charge in the upper right corner on the outside of the brackets. This is important. In mastering chemistry, the charges are shown, but the brackets are not shown. Do not text me and ask me how to put the brackets on an anion. Mastering chemistry can't do it. I don't know why they haven't figured out how to do that, but they haven't. So just put the charge in there, okay? So let's do the Lewis structure for sodium bromide, NaBr. So we've got sodium. How many valence electrons does sodium have? 1. So we're going to put 1 dot. And then we've got bromine. And how many valence electrons does bromine have? 7. So we'll put 7 dots. 1, 2, 3, 4, 5, 6, 7. Are these guys happy? No. But they can work together to make themselves happy. Sodium is trying to get rid of this electron. Bromine is trying to get one more to fill out her octet. So they come together and they cooperate. Sodium gives his electron to bromine. So I'll take that away and give it to bromine. Oh, that's a little crooked. Okay, I just moved the dot. When atoms gain or lose electrons, they become ions. If you lose a negative charge, you become a positive ion. If you gain a negative charge, you become a negative ion. And then opposites attract. Any questions? You like this better than quantum mechanical orbitals? Yeah.
Now, like for example, would there be any situation where you would have to do the equation versus this? Like, is there like a question I was going to ask for that?
Well, it might ask you to write a chemical equation representing this, and so you could do that like this. Sodium, well, I'm just going to stick with blue, plus bromine becomes sodium you could write it in equation form like that, where these are the original atoms, And what's happened here is that this electron has been transferred to bromine, and now we're representing sodium as an ion because it lost an electron, and bromine as an ion because it gained an electron. So Lewis theory helps us to predict the chemical formulas for ionic compounds. We learned how to do this by crisscrossing charges, but Lewis theory shows us why this works. So let's look at barium fluoride. So here we've got barium. How many valence electrons does barium have? What group is it in? It's in group 2. So it's got 2 valence electrons. And fluorine is in group 7, so how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. So here's fluorine saying, I need an electron. Does anybody have an electron I could have so I can be cool and go to the party or look like the in group? And barium saying, hey, I need to get rid of 2 electrons. Fluorine says, I'll take one of those electrons off your hands. And so a transfer occurs. So I'm taking this electron that was on barium and I'm giving it to fluorine. So I just moved the dot. Is fluorine happy now? Yeah. Fluorine also has a negative charge, so let's put brackets around that and a negative charge. What's the charge on the barium now? +1, because it lost 1 electron. Is barium happy? Nope. Not happy. If there's 1 fluorine hanging around, there's probably another one as well. So here, well, I'll just put her over here. Here's another fluorine atom. 7 valence electrons. Hey, I need an electron too. You like how they talk to each other? I can do this with atoms. I could never do it with Hot Wheel cars. And this barium is saying, hey, I need to get rid of this electron. Would you take this? Oh, sure, I'd love to take that electron off your hands. This is so stupid. Go ahead and laugh at me. It's fine. But you'll remember this. Okay, so I moved that electron from the barium to the fluorine. And now fluorine has a negative charge. And the charge on barium has gone from +1 to +2. This fluorine's happy, octet of electrons. This fluorine is happy, octet of electrons. The barium is happy because we took off the unfilled valence level, and underneath the new valence level is full. We can't see those dots, but we know they're there. And then we have attraction between positive and negative charges. You see how that works? And that's why barium fluoride is BaF2, because it takes a ratio of 1 barium to 2 fluorines to make everybody happy. You can read all kinds of odd things into that if you wish. Okay, let's use Lewis theory to predict the formula of the compound that forms between magnesium and nitrogen. So here's magnesium. How many valence electrons? 2. 1, 2. Are you okay with all one color, or would you prefer 2 different colors for the 2 different types of ions? Nobody has an opinion. I'll stick with 1 color. Nitrogen. So here's nitrogen. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. So magnesium is looking to get rid of 2 electrons. Nitrogen is looking to gain 2 electrons. So magnesium will give these 2 electrons to nitrogen. So I'm going to make that disappear and appear over here. So I moved 1, and I'm going to move another 1. Is everybody happy? No. Magnesium's happy. Magnesium got rid of his 2 electrons. Now he has a 2+ charge. because he lost those 2 electrons. What's the charge on this nitrogen now? It gained 2 negative charges. So the charge is 2 minus, but it's not happy. We can't stop until everybody's happy. What do we need? We need another magnesium to give another electron to nitrogen to make nitrogen happy. So let's bring in another magnesium. This magnesium also has 2 valence electrons. So this magnesium donates one of its electrons to nitrogen. Now the nitrogen's happy. Let's fix the charge. The charge is 3 minus. That's why nitrogen forms a 3 minus ion. It takes gaining 3 electrons to get an octet and to be stable. This magnesium now has a plus charge. So the first magnesium's happy, the nitrogen's happy. Is this magnesium happy? No. Needs someone else to take an electron. We're just dealing with magnesium and nitrogen, so that means we need to bring in another nitrogen atom. Magnesium says, well, you take this electron. And the nitrogen says, oh, I'd be happy to. These guys are a little more sophisticated. So we move that 1 electron from magnesium to nitrogen. Now the magnesium has a 2 plus charge because it lost both of its valence electrons. This nitrogen has a -1 charge. Is it happy? No, it doesn't have 8 electrons. And we can see the 8 a lot like we see 6 on a die, one of a pair of dice. 2, 4, 6, 8. Pairs on the top, the bottom, the right, and the left. This nitrogen isn't happy. We need another magnesium to give it electrons. So pull in another magnesium. This magnesium has 2 valence electrons. Nitrogen says, hey, I need 2 electrons. You've got 2 electrons. Let's make a trade here. Let's transfer. And the magnesium says, that's a great idea. Let's do that. So magnesium takes those 2 electrons and transfers them to the nitrogen. This magnesium now has a 2 plus charge. Oops. And the nitrogen now has a 3 minus charge. I think that's cool. We can see how that happens. The relationship then, the formula, there's 3 magnesiums and 2 nitrogens. What we learned before is by position on the periodic table that magnesium forms a 2 plus ion and that's nitrogen, forms a 3 minus. And then we did that crisscross thing to avoid doing math. And we ended up with Mg3 and 2. Well, it turns out this is really just kind of a trick. This is what's actually going on. Any questions? Do you see how it works? Yeah. How does it get more and then less? Are you talking about in the crisscross thing here?
No, from you know how you keep on putting the Mg.
Oh, how do we get another Mg?
Yeah.
Well, we've got magnesium and nitrogen reacting. We're going to have more than 1 atom of each. We're probably going to have 50 gazillion of each.
Every time you put Mg, do a whole other nitrogen.
Well, what I'm doing is I'm starting with 1 of each and seeing if that's going to be good enough, because we're looking for the simplest ratio. Is it going to be 1 to 1, 2 to 1, 3 to 2, whatever? So we tried there, and we didn't have quite enough electrons, so we had to bring in another one. But then we had too many electrons, so we had to bring in another nitrogen that needed electrons, But then we didn't have enough, and we think, oh man, we're just going to keep going back and forth all day long. No, it will end eventually. We brought in a third one, and now it came out even. So I only brought in as many as was needed for them to get together and all transfer and have their octets. When the compound forms, it's this times like Avogadro's number. You know, it's a huge amount. But this is looking at the individual atoms and how they interact with each other. Does that help? A little bit, kind of. Yeah, ask me in lab. We'll try again. Any other questions?